Yeah, hello and welcome to the last session of this school. I would like to take the opportunity first to thank the speakers for the wonderful and very clear lectures. Let me start with some announcements. Maybe you heard them already, or you surely did. So the live transcript will be automatically on automatically, and if anybody wants to turn it off, they can do so by clicking the live transcript button at the bottom of their screen. If someone asks a question verbally, it's recorded and live streamed. So don't raise your hand if you don't wish to appear in the live stream. I want to remind you of the communal board. And if you don't have a little link, you can ask Gemma for it. And that communal board will stay up even after the end of the school. So maybe one more thing, I will ask kindly the speakers to try to limit their talks to about 55 minutes so that we have time for some short questions. And also, if there are longer questions and discussions, whenever possible, it would be nice to leave them for after the three talks end. And let me see what time. Yeah, so it's a pleasure to have John King here as our first speaker. And he will talk the third lecture on exponential asymptotics for physical applications. And without further ado, I'll let John speak.
Thank you, Ovidio. So I'm going to eschew the usual general thanks and single out Ines because she has carried a significant load making sure this program functions as it should. So many thanks, Ines. So the plan today, firstly, as is probably already clear, I plan to demonstrate exactly the opposite level of technological competence demonstrated very ably by Phil yesterday. And incidentally, I thank Phil for organising this part of the spring school. So secondly, the material I'm going to cover is implicit in the title. I'm going to clarify the terminology shortly. So the majority of the talk will be on multiple scales, but there will be a chunk on matched asymptotics as well. So my strategy is the following. If you're new to asymptotics as used in applied mathematics, you'll have seen some pretty sophisticated applications, but maybe not the more basic ones. So I'm going to try and do some backfilling so that the two examples I'm going to focus on are textbook ones in terms of their real line analysis. But I'm going to continue into the complex plane, talk about Stokes phenomenon and so on, see what extra information may or may not be gained by going complex in these fairly standard examples. They will be nonlinear ODEs. So a bit of signposting for things to look out for. I suspect my viewpoint is slightly different from Gerald's on the extent to which nonlinear problems add extra difficulties, though I suspect our views aren't incompatible. So non-integrable nonlinear problems, the issue is not with the Stokes lines, because the Stokes smoothing is essentially a linear phenomenon. It's with the anti-Stokes lines. So in linear problems, they're entirely benign. You've got two exponentials that pass through each other without noticing each other. In nonlinear problems, they can lead to all sorts of complications. So as indicated, my approach will be to illustrate the kind of complications that can arise by doing two very specific problems. So symmetries are going to play an important role. They're often just implicit. I'm going to try and make them largely explicit. Nonlinear turning points where different exponentials have the same size, their role will be one of the things I'll focus on. So in terms of the jargon, there are two broad classes of formal asymptotic methods typically used in applications, and you can illustrate both of them by damped simple harmonic oscillator. And of course, there's no Stokes phenomenon or anything going on here. but it does clarify the basic phenomena. So the one at the top is the strongly damped case, where the epsilon is in the classical singular perturbation position of multiplying the highest derivative. The general solution is written on the line below. So it's made up of two components. So everywhere except in this very narrow region on the left, it's only the second exponential that matters, because the first ones become exponentially small. So the small term is only relevant in this narrow region, close to the left-hand boundary in this case. The terminology matching is to do with how you glue together the two different components of the solution when you can't simply write it down in simple closed form. Multiple scales in some sense is the opposite, where the small term effect is not a local one but a cumulative one over very large times, and you demonstrate that by very small damping, and then the solution takes the form recorded here, where you explicitly see that there are two timescales present when epsilon is small. There's oscillations here happening on the timescale little t is order 1, but a much slower decay on a much longer timescale. T is order 1 over epsilon as the prefactor. So that's the kind of jargon and the setup. The examples I'm going to do are both based on a non-linearly damped version of the same ordinary differential equation. So van der Pol wrote it down originally in the electrical circuit context. There's a misprint. I also noticed this week he applied it to heartbeats. Right, the significance of this as a model problem is if you draw the phase plane, there's a single periodic orbit, a single limit cycle. The other trajectories all approach that orbit. Rayleigh wrote down the potential version of this ODE in the nonlinear acoustics setup context. So symmetries. This is written on the fast timescale. I'm subsequently going to take epsilon to be small. And then I group them in two forms. So you can translate time by an arbitrary constant. So that's a continuous symmetry. It's time translation invariant. There are also two discrete symmetries. You can swap the sign of u, and that's reflected in the symmetry of the phase plane. And you can also swap the sign of the small parameter and run the thing backwards in time and leave the equation as it was. If I rewrite it on the slow time scale to look more like the classical singular perturbation setup, again, you've got the general continuous translation invariance in time, but the second discrete one looks different. U goes to minus U is the same. But a feature of matched asymptotics in particular is which scaling you're looking on determines how the symmetries that might arise in the small parameter look. So in the second case, it's symmetric in epsilon. Epsilon to minus epsilon takes it to itself. That's not true in the first. Okay, so what would you do for small epsilon? The first thing you try is simply expand U as a regular power series in epsilon, a regular expansion. So if you do that, you rapidly find what goes wrong. This slide records that. U0 does oscillate, but it doesn't capture any damping. Incidentally, I should comment that the damping changes sign here as U goes through plus or minus 1, which is why there's a limit cycle. It's a balance between positive and negative damping. Okay, so go to next order. Here's how the equation looks. You substitute in U0, solve this thing. Here's the complementary function. Here's the particular integral. There's a resonance effect in the particular integral that leads to something being, in the terminology, secular. So it's growing linearly with time compared to the leading order solution, which is purely oscillatory. Okay, so when little t becomes order 1 over epsilon, the first and the second term become of the same size. So there's a non-uniformity in the expansion, and you can't use it as it stands. So instead, you use multiple scales. So this slide goes into it. I revisit the symmetries, and the red ones are symmetries of the multiple scale setup. The green one is an exact symmetry, one we've already seen, of the original ordinary differential equation. So there are two timescales in this problem, as I hinted at with the corresponding linear problem. So the fast timescale, the oscillatory one, is given by tau, which is an order 1 rescaling of t. So that saves a lot of subsequent algebra if you introduce that from the start. The slow timescale of damping is this capital T timescale here. So I apply the chain rule and write the ODE in terms of both those variables, and that's recorded here. Okay, so if you're indoctrinated into multiple scales, you may not be conscious of what an odd thing that is to do. Right, I'm pretending an ODE is actually a PDE in two independent variables that have nothing to do with each other, whereas of course they're simply multiples of each other. The reason that point doesn't generally get made is it's an extremely effective method. Expanding in powers of epsilon, turning the handle, it's fairly routine to construct the solution to any algebraic order you like, admittedly at the cost of a lot of algebra. There are alternative methods. There's a pile that generally get lumped under averaging. There was a group of physicists tried to develop renormalization approaches to the same kind of setup a few years back. I haven't followed whether they went anywhere. The reason I'm raising that is I believe the two-timing approach, the multiple scales approach, is by far the most powerful way of getting arbitrary terms in the expansion on just the first one or two. Okay, so what are now the symmetries? Well, now magically we've gone from a single time translation invariant to two. So this doesn't explicitly involve either. I'm sorry, there are misprints here. These little t's should be tors. It doesn't involve either explicitly tor or big T. So it appears to genuinely have two translation invariants, whereas the original setup only had one. Because of that, I can do an initial value problem where I'm going to start all the solutions from the unstable spiral at time minus infinity. And I can construct the general solution inside the limit cycle by this single initial value problem by additionally using these translation invariants. So this does generate a two-parameter family because of the two translation invariants. The change of sign, reflection of U symmetry is still there. The change of direction of time involves only one of the time variables, tor, when you swap the sign of epsilon. So this isn't a symmetry of the original ODE because capital T and tor are actually proportional to each other. But as far as the PDE is concerned, this is an exact symmetry. Okay, so but the red properties are not shared by the exact solution, but they are shared to any algebraic order in the expansion because you can construct any order in the expansion by expanding this equation at the top in powers of epsilon. Okay, so inherited from these various symmetries are properties of the solution. So there are two complex plane symmetries. Shift tor by pi, you swap the sign of U. Shift it by 2 pi, and it is a periodicity condition. And there's also an imaginary periodicity in capital T. So I should emphasize this isn't doubly periodic in the sense that elliptic functions and things are. This isn't, neither of these periodicities is shared by the exact solution. Each of them involves an individual timescale into which you split the original setup. In terms of this final red symmetry down here, if it follows that the nth term in the expansion picks up a -1 to the n when you swap the direction of tor. So being aware of these properties gives pointers to what's going on, simplify your algebra, but also have more fundamental relevance. Okay, one way to see there's a fly in the ointment already, which is not to do with beyond all orders in fact, but sort of has the same root cause, is over here I promised that at any order the thing is periodic 2 pi in tor. If you do a separate analysis of the limit cycle itself, which requires a different method, you find the leading order result I've just implied is correct, but the first correction term in the expansion is wrong. So the periodicity to all orders in tor I've alluded to, there is something amiss with it. So now the algebraic expansion, again, this is at textbook level, and then I'm rapidly going to go over to the complex plane. So to apply the standard multiple timescales approach to constructing a uniformly valid solution to the ODE, I expand, the dots are going to be d by d tor, the dashes are d by d big T. Leading order problem is the same as the naive expansion, but now you have to remember that these are just little tor derivatives. So the solution has the constants of integration are actually functions of big tor here. So this is the general solution of leading order. The correction terms, the first three terms are identical to the naive expansion, but there's now one extra one which is going to save us, and that's from this combination, this mixed derivative in the PDE version of the problem. Okay, so some of the terms are as before, which are the first two here, but these two new ones come from this additional term from multiple scales. And now I can kill all the terms that would otherwise resonate. I group together all the blue ones, the sine tall ones, to enforce that the amplitude has to satisfy this ODE, and the cos terms, there's actually only one of them, so the phase doesn't vary. So another thing, if you're indoctrinated in multi-scales, this probably never occurs to you, is I've gone from a nonlinear second order ODE to a nonlinear second order system. So you may wonder what you've gained in general. It's clear in this special case because it's a very simple system. But the much more general statement is that Tor translation invariants get inherited by the fact that this system has to be invariant under translations of phi because of the grouping here. So phi can only appear as phi dash, which means the A0 equation has to decouple. So this reduced system is necessarily much simpler in structure from your starting point, even though it's of the same order. Okay, you solve that nonlinear ODE for A0 to give the expression on the top of this screen, where I've imposed the initial condition I referred to. Okay, so that kind of completes the textbook version of this problem, which is done to death. And now I go complex and see what extra things are going on, which are hidden by the real line analysis. So the first thing to do is, having established the real line solution, you might want to use that information to analytically continue vertically away from the real line. And there's an immediate issue in doing that. Here's the cos Tor. As you increase Tor, this term becomes exponentially large. And specifically, if I shift Tor by this amount in the imaginary direction, it picks up a factor 1 over epsilon to the half, which pulls in the nonlinear term at leading order. So here, this ends up being the matching condition, which informs this rescaling. Right, this will be a matched asymptotic argument, and I'll do another of those in a broader context later. But this rescaling then converts the original ODE into this form recorded here. Okay, so you can analyze this in the phase plane. Some signs have changed from the original problem, and in particular, the nonlinear term is pulled out more explicitly. Matching back towards the real line, the thing decays exponentially. But you draw the phase plane and you see this thing blows up along lines on which ρ0 is real. In between the branch cuts that are generated by those blow-ups, ρ0 is in general complex. But this little schematic at the bottom indicates what's going on. There's an entire line of branch cuts which kind of hinder understanding of what happens when you go off into the complex plane. Okay, so that's a description of how the exact solution, the true solution, behaves. But recalling we're splitting the dependence into capital T and Tor, I've got another way to look at things, and that's on the next slide. So I'm now going to continue horizontally from capital T is minus infinity, rather than vertically away from the real axis. Right, so in general, if you've got the solution on the real line, that's the only information you've got to start your analytic continuation, assuming you don't have an analytical form for the solution or whatever. With multiple scales, you've got extra tools to play with. So I can generalize the symmetry properties I mentioned at the start in terms of periodicity. If you go up a quarter period, so pi I, you find U becomes pure imaginary on lines where T hat is real. So you've still got a real ordinary differential equation. The signs change, which is reflected in this different form for the slow variation, but everything is real. So that is valuable, right? Everywhere else where you can't write the solution as a real variable, the problem is in effect fourth order, but here it's second order, so you can do the phase plane. Okay, so here's how the solution looks like along these rays, T hat real. It does blow up at finite T hat, which didn't happen on the real line. On the real line, everything looked innocuous. Now we have got a problem, and now we've got a nonlinear turning point. So if I look close to this blow-up point, which involves this rescaling here, where t star is 2 log 2 to cancel the quarter. This thing blows up like 1 over the square root. The rescaling that captures that blow up scales t hat with epsilon. And then you notice that that's exactly the same as the original time scale. So what's happened now is we've gone away from the multiple scales, the 2 timing, to having a single time scale again. And the nonlinear turning point problem embeds that single time scale and makes the original setup reflect the fact that we really have an ODE, not a PDE. Okay, I'm being slightly sloppy to save myself time. If I've now lost one of the 2 translation invariants. So by rights, I should slightly generalize things here to keep it general, but this will suffice for my purposes. So the nonlinear turning point problem under these rescalings is recorded here. The nonlinearity again comes in at leading order, just as it did on the boundary layer on the previous slide. Here's the far field behavior as you go backwards. I'm always thinking of integrating from left to right. And I've written the cosh thing in this form to remind you that even though this quantity is order 1 over epsilon, in terms of the cos, you think of it as order 1 because of the periodicity of the cos. Okay, so this is the nonlinear turning point with its leading order far field. But if you do a more detailed analysis of this turning point problem, you find there are exponentially small terms born in the far field. And I'll in effect come to those next. Okay, so as always, turning point generates Stokes lines, and we'll see their implications shortly. Okay, so now I'm on to factorial over power, as we've seen in many other contexts. So as Phil in particular elaborated yesterday, if you look at the behavior for large n, you need to get used to which terms you can keep and which you throw away. So it turns out this term's got a single dash derivative, so it brings down an extra factor n from the derivative of the denominator, which keeps the factorial of the same size as the left-hand side. Similarly, 2 derivatives here, but a shift of 2 makes this the same size as well. And the 3 terms that are 1 power of n smaller are the remaining 3 I've kept. And then there are more that are even smaller. So you use the usual Liouville-Green ansatz as recorded here. Here's the singulant, factorial over power. The prefactors I'm going to need to extract by going to the next order. Okay, so the leading order problem is recorded here. So this isn't quite like the standard factorial over power tail calculations where this equation would just be an iconal equation, an algebraic equation for chi dash. And that's because there are 2 timescales involved. So the slow variation appears only as chi dash, but we've still got the fast variation in here. So you want to think of this as the iconal equation coming from this as an eigenvalue problem for B naught or equivalently periodicity. And that requires chi to take this form, where n is an integer and t star is where the nearest singularities are. Okay, so that gives me the singulant in this large n expansion. To get the prefactor, the B naught, I have to go to next order, and I'll do that on the next slide. So grouping together what I've got so far with this form of chi, I extract the Tor dependence of B naught, sorry, yes, the Tor dependence, but not the capital T dependence. So here's how B naught n looks for the nth mode. So the tail contains all the harmonics, which is unsurprising because each time you increase the order, you pick up more and more harmonics, and we're doing little n goes to infinity here. But because of this capital N and the chi to a large power on the denominator, the tail is going to be dominated by the first, the fundamental mode, n is plus or minus 1. So I've written them down separately at the bottom. The reason to do that in part is to make very explicit the fact there is this kind of shift from where we started. We started with the cos Tor, we've shifted by an e to the plus or minus I Tor in getting B naught. Okay, so next slide will determine the prefactors, the capital T dependence reflected in alpha n and beta n. Okay, so go to next order as prefigured in the previous slide. The left-hand side is the terms we had for B naught, as always. the right-hand side, there are these extra forcing terms. We've constructed B naught except for its Tor dependence. So you substitute in. If you do that exactly, you get the expressions in curly brackets. You then have to do a lot of stuff with multiple angle formulae. Okay, so this thing here gives a sine 2 Tor, and then you lump it in with the cos Tor to give a sine Tor, and so on. So if you do that, you get the line below, where I've kept all the terms in sine Tor and cos Tor, but thrown away all the higher harmonics. Okay, so to make this non-secular, to avoid the resonance, I need to kill all the sine terms and the cos terms, but the other ones don't generate any secularities. So that fixes ordinary differential equations for alpha and beta. And at this point, you've got to check you've done your algebra correctly. If you look at the beta n equation here, you'll observe, if I go back, it's beta n satisfies exactly the same equation as A naught. Moreover, if I differentiate this once with respect to t, capital T, the A naught cubed gives a 3/4 A naught squared, and that appears in alpha n. Okay, so alpha n is proportional to A naught dash, beta n is proportional to A naught. Right, you expect that for reasons I'll say on the next slide, so that there is a very strong check on your algebra at this point. Okay, so I've described most of the behavior of the tail now. There are three things I haven't. Mu and nu will be the Stokes multipliers. You've seen algorithms for calculating those at various points, and I'm not going to do those. I'll just leave them as constants that can be determined. The other quantity I haven't determined is mu, and slightly unfortunately I've used mu for two different things. But mu will be the, mu appears in the form of the singulant and of the factorial. So how do I get mu? Well, this summarizes the information I've gathered so far. Yeah, I suspect those slides are in the wrong order. No, maybe not. Maybe I will stick to my original order. I'm going to get mu on the next slide. So firstly, I'm going to use the standard recipe for what a divergent tail like this turns on. So it's recorded in the top line, the information I've gathered so far. If you use the standard recipe, the thing that turns on through an error function, and I'm going to avoid doing the details of that, is the second expression on this slide. And now again, and I think most revealing of all in terms of the role of asymptotics beyond all orders in these multiple scales problems, is the way it links back the two original scales. Right, there's a capital T over epsilon in the exponential you've turned on. That is exponentially small because of this e to the minus n pi over epsilon. But this capital T will precisely at leading order cancel this tall term. Okay, so crucially, the two timescales are not independent as far as the switching on calculation goes. So again, you're respecting the fact that the PDE you're dealing with is actually an ODE in disguise. Okay, so doing that cancellation, this expression simplifies to this one here. This is what I turn on. It is exponentially small. And the reason I know the arithmetic has been right is leading order solution was A naught cos Tor. So its capital T derivative is this one. Its Tor derivative is this one up to a sign. So actually that should be a minus sign, shouldn't it? So the two quantities I've turned on are simply the reflect the original two time translation invariants. This thing is an exponentially small shift in the origin of capital T. This is an exponentially small shift in the origin of Tor. Okay, because as I commented, those two translation variants capture the general solution. They're the only things that can be turned on. So as I say, there's a very strong check on your arithmetic at that point. Okay, so as I've already forewarned, the thing I haven't yet calculated is this mu here. And that involves tracking the singularities through the relevant various orders. We've seen from the U hat calculation that U naught has a square root blow up. UN, you get one extra power each time you go to next order. So it's this form, A naught and A naught dash therefore have these singularities. So if I go back and compare this form with the expansion, the singularity there multiplying the singularity there has to agree with this singularity of UN. and that picks two different values of mu for each of the two terms in the expansion. So here, in rough or ready terms, are the leading order expressions for the two things that get turned on. Okay. Okay, so it's not very dramatic. Something important, sorry, something non-trivial happens in the complex plane associated with the Stokes phenomenon. It isn't particularly dramatic in this example. It is more dramatic in others. But in particular, I've broken all the red symmetries from before through exponentially small terms. And one way of flagging that very explicitly is to think in terms of what my red symmetries implied at every order about this solution U. If I stick t equals 0 into there and look back at the symmetries, it says that the value of U at the origin should be a symmetrical function of epsilon. In other words, a power series in even powers of epsilon. That's not the case, but the only level at which it fails is this exponentially small term, although it is an essential singularity, of course. This is very close to things that happen more importantly, as I say, in other contexts. The one I've flagged here is adiabatic invariance, so that there's problems where there's a quantity that only fails to be invariant by an exponentially small term in a very similar fashion to what's happened here. Okay, so that completes the multiple scales example. I'll come back to multiple scales at the end. So the second example I'm going to do is exactly the same ordinary differential equation, but in the opposite limit, the strong damping limit, where you see relaxation oscillations. This is a matched asymptotic problem. There's multiple regions indicated in this picture here, which I'm going to talk you through subsequently. Different dominant balances apply in each region, and the matched asymptotic game is to solve them, find leading order solutions in each of them, and then match them together smoothly to construct the entire time evolution. So incidentally, one reason I'm doing this example is you've seen a lot about airy functions. Here's an example where you get them in the wild in a context you might not have expected to see them in advance, because it's not obvious how an airy function sits within this nonlinear ODE up here. So this has been done to death on the real line, but I'm going to go into the complex plane. I am going to do one thing which is non-standard, which is the initial value problem I'm going to take will involve only the slowly growing exponential as time goes to infinity. The much faster growing exponential I'm going to exclude, and that's why this thing is a beery rather than airy. So the asymptotic structure is slightly complicated. It's recorded here. The symmetries for this setup, which is partly why I'm doing it, are exact. There's a 2 pi I symmetry in U as you go up in the imaginary direction. And if you go a quarter of the period up, U is entirely imaginary. So again, one will have a real ordinary differential equation along that ray, which helps make sense of things. Okay, so I'm going to talk you through the various regions 1 to 6. So I'm going to have to keep flipping back and forth. So region 1 is how we start to grow from this t goes to minus infinity behavior. To get it, all I do is cross off the epsilon terms, and I get a first order ODE. Non-linear, but classical for singular perturbations, you lose the highest derivative. Okay, so there's what it is at the top. It's separable, so you integrate it in this form. It has got branch points where this thing becomes degenerate, and they're located at these locations where n is an integer. And one of them is real, and that's going to lead straight into region 2. Okay, so already it's singular along the real line. So region 2, the scalings you can deduce from the behavior of this one as u approaches 1. You have to scale u with 1 plus epsilon to the third. You have to scale t with epsilon to the 2/3. So I'm reusing tau to mean something completely different. If I rewrite the original ordinary differential equation exactly in terms of these new scalings, it takes this form, and then I cross off everything multiplied by a positive power of epsilon. So that's a game I'm going to apply repeatedly without making it explicit again. So you have to get the scaling right. Once you've got the scaling right, you cross off all the small terms and you're in business. So this is actually a nonlinear turning point scaling again. Cross off the epsilons. This is the ordinary differential equation you get. You can integrate it once. So to take this form, as long as you get the origin of Tor correctly, it is Riccati. So this is where you're going to get Airy from by this standard change of variables to go to here. Okay, so this is sort of doing Liouville-Green in reverse, right? You're going from Riccati to linear rather than vice versa. So the general solution to this is a sum of Airy and Beery. Here, because I've killed off the fast exponential at infinity, the solution you want is the one without it on the real line, and that's precisely the Beery. There is exponential sensitivity in this. There is something slightly interesting going on here, which I'm not going to get into the details of, but I'm having to kill off the subdominant exponential at minus infinity to get this unique solution. So here's the form for V0. Okay, so what does that tell us? Well, we know the Airy function has the Stokes phenomenon. So the Stokes line tracks back along the real axis. The anti-Stokes lines come up at angles plus or minus pi by 3 to this one. This thing is singular wherever Beery is 0. So there's a line of them on the real axis, but you don't see any of the others once you've hit the first one. And then there's rows that approach the anti-Stokes lines at infinity. Okay, so I'm going to need to worry about all those complexities in a minute. Okay, to deal with it, so I do want to discuss the Stokes phenomenon associated with this Stokes line, which is the next slide, right? So Adri alluded to the fact that Jeffreys got to WKB 3 years before they did. They were actually 90 years off the pace. So historically, it is deeply weird that most people call it WKB. So Liouville and Green both published it independently in 1837. Again, to follow approach Adri started, Green is buried in Nottingham. His windmill is there. He was almost entirely self-taught. So this is the kind of ansatz Liouville and Green adopted to pick up the exponentially dependent terms. There's the algebraic expansion in between, but I'm safe in doing this because I know about the Stokes phenomenon. So here's how my expansion looks, and then I need to go back to this original ODE. This thing will bring down a 1 over epsilon times sigma dot squared. This will bring down a 1 over epsilon times sigma dot. So my exponentially small contribution sigma satisfies this ordinary differential equation. I can solve it in terms of U0 rather than in terms of T, but I already know U0 in terms of T. So it takes this form here. Okay, so you can work out what kind of quantities get turned on as you cross the Stokes line along the real axis, and we'll see what role they play in a minute. I flagged as a sort of minor point here, sort of slightly intrigues me that there is an issue of causality here. To understand the exponentially small terms at infinity, in particular to know about these 3/4, you have to integrate forward until you get to the turning point and then go back again, solving this first order ODE in the wrong direction to get the behavior at minus infinity. So if anybody has anything profound to say about this, I'd very much like to hear it. Okay, so once I've got sigma, the significance of it is where real sigma is 0, rather than being negative, this term becomes comparable to the leading order one. In other words, we have an anti-Stokes line, and that's what the next slide is about. So the periodicity I've alluded to means you've got this array of Stokes lines parallel to the real axis. The anti-Stokes line, I believe, looks like this purple curve. So someone more competent than me, if they wanted to construct it numerically, and it would be rather straightforward from these formulae, I'd very much like to see exactly what it does look like. But there is this anti-Stokes line on which the nonlinearities are going to come in and cause significant difficulties. So to be clear, the additional term, the Liouville-Green one, is exponentially small to the left of the purple curve and exponentially large to the right, which means it's not actually there to the right. It would be in a linear problem, But here, the thing that happens across the anti-Stokes line completely changes the structure. Okay, I've already indicated that I've got a good way in here, that I know halfway along here, for imaginary t is pi by 2, I can solve the thing as a real ordinary differential equation, and that follows from the symmetry properties. So I hit the anti-Stokes line at some constant value t star that I can determine. Indeed, I have even determined the number there. Okay, so what's the local behavior across this anti-Stokes line, which is intrinsically nonlinear? Here's what the original equation looks like when I go from u to u is I u hat, and I shift t up to give t hat. And then I look local to this purple curve. I blow up, I magnify by a scale epsilon, and then cross off the negligible terms, as I've already been doing. And you integrate once. Here's your first order ODE. Okay, the right-hand side, there's an abusive notation here. The right-hand side is just the constant you get from the solution in region 1. So I know the value there. I know how it decays exponentially to the constant value as t hat goes to minus infinity. So it's easy to analyze this thing in the phase plane, or indeed just integrate it. So one infers from that this function blows up on a line of, use the periodicity, a different kind of periodicity of this initial value problem recorded at the bottom, which tells you that it blows up at points separated by this distance, including along the real t hat line. So their order epsilon spacing in the original variable. So the anti-Stokes line generates a vast array of branch cuts. So you get sent off into large numbers of different Riemann sheets if you continue to try to integrate from left to right, according to this picture. As a check on self-consistency of everything, if I go back here, there is this line of singularities from the Beery. They get closer and closer together as the number of zeros becomes large, and I record for reference how they go. They locate, the nth zero is located at a distance tor is order n to the 2/3 from where you started, and they get closer and closer together, so n to the minus 1/3. So if capital N is order 1 over epsilon, you have that large number of zeros. T is a distance order 1 from the nonlinear turning point here, so you're in the purple territory, the anti-Stokes line territory, because the spacing between them has gone to order epsilon on the same scaling. Okay, so the whole thing hangs together. The analysis I do of the anti-Stokes line matches nicely with the analysis of the nonlinear turning point. Okay, so I now go back to the real line. So I now need to go back to refer to this rather complicated matched asymptotic structure. So I quickly flip down from the value 1, which is where the Beery ends up at, to the value -2. So the scalings that allow you to do that are recorded here. So that's in terms of little t. So you're magnifying little t, but actually you're also magnifying tor. So tor was already a short time scale. You're on an even shorter time scale, as recorded here. The dominant balance, having done the rescalings, is recorded here. To match into the Beery, you need this. You integrate once, and here's your first order ODE, which you can integrate. And it's essentially exactly the same structure as the anti-Stokes line structure I've just described. So it generates an array of singularities, but they're almost all on other Riemann sheets, again, when integrating left to right. So the picture to have from this inner analysis for capital T is order 1, is that within this channel, U0 goes to -2, as I promised from the real line picture, and is well known. But if you go off to infinity in any other direction, you match into Beery. So you have this 1 over -t dependence. But henceforth, we're going to be restricted to this channel if we want to know the real line behavior. Okay, I do the rest rather quickly because I don't want to bombard you with too much information, but there are little bits of extra information from them. Specifically, 5 is going to be airy rather than Beery, and that has little knock-on effects. Once you get beyond 6, 6 is just the mirror image of 3. The next one's the mirror image of 4, and so on. So you don't need to do any more. You've locked onto the limit cycle, in other words. Okay, so region 4, this very rapid, this slower rise up from -2 to -1 follows the analysis I did coming down to +1 in the previous case, and again generates singularities. The only one I want to say anything significant more about is the second region of turnaround. Okay, so here there was a corner. You go from increasing to decreasing. Here you just smooth off the way you're increasing, which means you get an area rather than a Beery. Okay, so the scalings are equivalent to those before. The ODE is equivalent, and therefore the linear one is, but you want the other solution to the linear problem. So it's the area function solution there. And that's because the matching back has a different sign for the reason I've just alluded to. Okay, so this intends to complete the picture of this, the analysis of this case. So to rewind slightly, the statements I'm trying to make is that for the multiple scales problem I've done, it really does have payoff to go to the complex plane. I would argue if you don't do it, you don't really understand the problem. For the second one, the matched asymptotic one, it turns out that there isn't very much payoff. The complex plane is so complicated and generates so many Riemann sheets you're not interested in that it's not actually worth the effort. And the way to see that is actually that the turning points are on the real line, whereas in the multiple scales one, they were in the complex plane. But to make that more explicit, I used this picture. So 3 was Beery. Here 6, we're magnifying again, we've got airy. So airy, you might worry about the Stokes line phenomena, but I want to emphasize that the Stokes lines associated with airy actually play no role at all. The Stokes lines themselves are on different Riemann sheets. They're in the far field, so they're outside the branch cuts you've generated. The anti-Stokes line is in the channel you've got, but you hit region 6 before the airy function generates this anti-Stokes line. So that anti-Stokes line is not really there either. Okay, so I complete this example by recording. You then just get this repeating pattern. And if you want the real line solution and you want to integrate left to right, you can't go beyond this little channel. Okay, so I'm nearly at the end of my time and I have a few further things to say. So I might have done Kuramoto-Siversinski, and I believe you've looked at that in the tutorial session and John Chapman said a bit about it. So I want to highlight the differences and the similarities. So Kuramoto-Siversinski is a PDE, it's a model problem in pattern formation that's used in combustion theory and elsewhere. Travelling waves satisfy the ordinary differential equation recorded at the top. So there's 2 types of potentially of heteroclinic. The monotonic shock would take you from -1 to +1. If you do the boundary condition count that John Chapman's referred to again, but I'm going to give a different nuance on it, you need to kill 2 exponentials at each end. And translation invariance means it looks like you've got 5 boundary conditions on a 3rd order ODE. But actually, if you think in terms of odd solutions, you've only got 4. So then you can think of it as an eigenvalue problem. So there will be a solution for particular values of epsilon. Unfortunately for Kuramoto-Siversinski, they're for epsilon squared negative. But John did an example with a different nonlinearity where epsilon is positive. The other type of heteroclinic is this oscillatory shock, which I've done a beautiful diagram of here. So it goes in the other direction from +1 to -1. You only need to kill off 1 exponential at each end. So you've got 1 boundary condition at each end. And whichever way you view it, you've got 3 boundary conditions on a 3rd order ODE. So it suggests there may well be a solution. It turns out that there are 2, at least for small epsilon. They're both odd. 1 is increasing as you go through the point of oddness. 1 is decreasing. So that's the preamble. The important points of comparison and contrast are recorded on this slide. So again, the double translation invariance causes confusion and you need to be very careful what's going on. Because of it, it implies that if you've got a solution, you've got a 1 parameter family of solutions, even given the single translation invariance the original ODE has, because you use the second translation invariance. They almost all of them fail due to an exponentially small term. that links them together, just as the two translation invariants were linked in the simpler problem I did do. They're linked at the turning points, and they're linked at the beyond all orders factorial over power Stokes switching calculation. One of the reasons to focus on the second order case, I came to the conclusion, was you know in advance everything that can be turned on because they're associated with the two translation invariants, which here are the variation with respect to the fast scale and the slow scale again. So those are the two of the things that can be switched on, but it is a third order, and that there is a third one, and that's much more important in this third order case because it grows exponentially. And that's the thing that generates the failure of existence recorded above. Okay, so the things that get turned on by either the monotonic or the oscillatory shocks are exponentially small, but they grow exponentially. So eventually they become of order 1. In other words, you come to an anti-Stokes line, and doing the anti-Stokes line analysis in that case allows you to glue different shocks together. And in particular, for example, if you have one up shock and one down shock, you end up where you started. You generate a homoclinic. In other words, you generate a solitary wave. Final point is a slight conundrum, which I find interesting with these higher order cases. If you track back, the nonlinear turning point is in some sense straightforward to capture with multiple scales, but if you track back to what's going on with the true solution, you find it's actually beyond the natural boundary in the analytical continuation of the true solution. So there's absolutely no way you can get there as far as the true solution is concerned. So there's another slight philosophical conundrum I've recorded at the bottom there. That turning point is certainly not present in the true solution because you can't get there. But it is responsible for the properties of the tail of the expansion of the true solution. And therefore you can regard it as responsible for the Stokes phenomenon. Okay, so that's Kuromoto-Sierpinski and some of the similarities and differences you see when you kind of use these methods for real in higher order problems. I conclude with one more slide. So these are sort of my top tips, which are maybe intended to be taken slightly more seriously than the Viz ones. I sort of take the view it's always worth a go continuing into the complex plane. It may not pay off, but if it does, you may get quite a lot of extra insight. And I've argued that that is true of the multiple scales problem, where you really understand what's happening with the two different time scales, but isn't really true on the matched asymptotic problem, the particular one I've chosen. And that's because the turning points are on the real line. In terms of applying these formal asymptotic techniques, one point that's been implicit, but I tried to sort of major on, is that different scalings apply in different regions. But if you can identify all the regions and get the scalings in the right place, in the right form, and therefore the epsilons in the right places in the ordinary differential equation, or PDE or whatever you've got, you have won half the battle, because then it is just handle turning of constructing expansions in the relevant powers of epsilon, or logs and things if they've arisen. It's worth emphasizing that there are more ways that can happen in a nonlinear problem than a linear one, because if you scale the dependent variable in a linear problem, if it's homogeneous, then nothing happens. But if you rescale the dependent variable in a nonlinear one, you can completely change the balance. And we've seen that happen. My final point, a claim I would make is it's important to try and derive universal methods, but I would claim they're limited in the sense that you do need problem-specific approaches as well. And in part, they're associated with the very complex plane structures, which are branch cut structures, which in turn reflect the nonlinear turning points and the anti-Stokes lines. So things like factorial over power and error function smoothing are universal. Other aspects aren't. Nonlinear turning points, you can get all sorts of different types in different problems, and we have seen that by doing different problems. Panlevane maybe comes up more often than you'd expect, but it's certainly not universal. So those are my concluding remarks. I think I'm pretty much on time and we'll finish there. So thanks very much.
Yeah, so let's first thank John for a very, very nice talk. And we have about 5 minutes for questions, comments. Let's see, there is already a question in the question and answers. John, can you see it?
No, I can't, but let me try. Physical interpretation of nonlinearity, to be honest, I'm not sure. It's not a context I've looked in detail. If you look up Van der Pol on Wikipedia, you'll see the electrical circuit. Mathematically, it's pursued for the reason I've indicated, the balance between positive and negative dissipation give you the interesting effects which are associated with the limit cycle.
Let's see. Other questions, comments? All right. Yeah, I have a very quick comment. I mean, there are some very recent developments in two-scale problems, which effectively eliminate the fast variable for most of the analysis. Okay. But that's not the right place to sort of discuss. Maybe we can chat at some point during the program.
That would be great.
Maybe we can also involve Saleh Tanvir in the discussion. You know him very well, I suppose.
Sure. Thanks, video.
So maybe you can
read the question. So the answer is yes. So where the leading order problem is nonlinear, the period of the leading order problem is a function of the slow variable. So there's a method normally called Kurzmak's method, where in effect the fast variable is a nonlinear function of a slow variable. You also need the same thing in linear problems in the adiabatic invariance thing I've alluded to. One thing I haven't talked about is there are certainly cases where you need more than 2 timescales, and it's not entirely clear to me how to characterize how many timescales you need, which is why I did those initial value problems from -infinity, where it is very clear.
Okay. Let's see, do I see anything else here? Well, if not, thank you very much, John. I mean, that was really beautiful. We have a couple of minutes of break until the next talk.